Today, we're going to talk about a really fundamental shift in how we think about designing AI systems. It's a story that's all about moving away from this idea of handcrafting every single component, like a bespoke machine, and moving towards creating these reusable, reliable frameworks, or scaffolds, that can be scaled and adapted in really predictable ways. And this isn't just some minor technical update. It's a deep change in the whole philosophy of what it even means to build intelligence.
So, this leads to a really interesting question. What does an AI architect actually do today? I mean, if they're no longer sitting there drawing up a super detailed blueprint for one single unique machine, what are they building instead? Well, the answer to that has changed, dramatically over the last decade.
In this slide, this really gets to the heart of the whole mental model shift. The old way of thinking, it was all about authoring a very specific machine. You'd embed your own expert judgment into every single layer. You were creating a detailed blueprint. But the new view is totally different. It's about defining a reusable regime. It's about putting your trust in a repeatable scaffold. So it's less about one perfect blueprint and more about creating a family discipline, a set of rules that can generate a whole population of really good models. To get why this shift happened, we've got to rewind a bit.
So let's start back in the age of bespoke machines. This was a time when, honestly, every major neural network felt like its own unique, hand-built object, just packed with all these specific choices that were pretty hard to generalize.
This whole period is really defined by a few key moments. So, in 2012, AlexNet was this huge breakthrough. It basically proved that deep learning could win, but its design was super specific. It was a successful object, for sure, but it wasn't a repeatable formula. Then, just 2 years later, in 2014, the field kind of split. You had VGG, which argued for simplicity and discipline, showing that just repeating simple 3x3 convolutions could be incredibly effective. But at the exact same time, you had Inception, which argued for the opposite, for complexity, building these modules with a bunch of different operations, all happening in parallel.
And this slide just illustrates that crossroads perfectly. The big question in the field was, should our architectures become more regular and disciplined, like VGG? Or should we be embracing more local complexity and variety, like Inception? And back in 2014, both answers seemed pretty plausible. The path forward wasn't clear at all. And this tension actually exposed a much, much deeper problem.
And that problem was what we now call the deep network paradox. See, as researchers were trying to build more and more powerful models by just stacking more layers, something really weird and counterintuitive started to happen. The models, they started to break.
This quote from the 2015 ResNet paper just nails the core of the paradox. Deeper networks, the ones that should have had more capacity, were actually showing higher training error than the shallower ones. This was baffling. A deeper model should, in theory, be able to at least perform as well as a shallower one, right? But for some reason, it just couldn't.
And let's be super clear here. This was not an overfitting problem. The deeper models were failing even on the data they were supposed to have completely mastered. This pointed to a really fundamental optimization issue. The training algorithms were basically getting lost in an increasingly complex landscape, and they just couldn't find the right path downhill. Repetition by itself was not enough.
And that brings us to the hinge of this entire story. A simple, elegant idea that solved the depth problem and unlocked the ability to train truly massive networks. This was the moment the scaffold was born. And the solution came down to this one simple change. Instead of forcing a layer to learn a complete transformation, y equals f of x, the residual connection asks it to learn just a correction, f of x, which then gets added back to the original input. This little tweak had massive global consequences.
So this simple equation, it changes everything. First, layers go from trying to do a full rewrite of their input to just making a refinement. Second, and this is absolutely critical, it preserves a direct path for the original signal x to just flow right through the network, undisturbed. And the result? The architecture becomes this stable, trainable scaffold. Suddenly, depth doesn't feel like a fragile chain anymore. It feels like an accumulation of small, stable improvements.
And later research confirmed exactly why this worked so well. It created this clean highway for learning signals, the gradients, to flow backwards through the network. This effectively smoothed out what we call the loss landscape. That's the terrain our optimizer has to navigate, making it so much easier to find a good solution. The field had finally figured out how to make depth work.
So, with the problem of depth finally solved, this powerful idea was then packaged into a repeatable block that would go on to change not just one corner of AI, but the entire field. And that's when the transformer block entered the scene.
So what is a transporter block?
Well, yeah, it's famous for self-attention, which lets every element in a sequence look at every other element. But what's just as important is its structure. It packages that powerful computation inside the exact residual scaffold we were just talking about. And that is what made the blocks so repeatable, so stable, and ultimately so incredibly portable.
Okay, so this raises a really interesting question. If you build a massive model by just stacking hundreds of these identical blocks one after another, does the model end up just doing the same thing at every single layer? Is its function totally uniform?
And fascinatingly, the answer is no, not at all. When people analyzed models like BERT, they found that even inside a perfectly uniform architecture, functional specialization just emerges during training. Different attention heads learn completely distinct jobs. Different layers also specialize, forming this sort of pipeline from low-level to high-level understanding. The architect didn't have to design any of this. They just had to create the scaffold, and training found the structure all on its own.
Now, the Vision Transformer showed just how portable this scaffold really was, applying it successfully to images. But it also taught us a really crucial lesson in humility. This portability, it's not magic. The scaffold only really works its magic in new domains when the training regime, the amount of data and compute, is massive. Without that kind of scale, more specialized architectures can still win.
And this brings us right into the modern era, where the AI architect's job has elevated once again. They are no longer just designing models, they're designing the entire system of creation.
The new object of design is now the design space. So instead of one blueprint, the architect defines a whole family of possible architectures that are all governed by a shared set of rules. Work like Neural Architecture Search and RegNet made this super explicit. The goal is to define a space where lots of good models can live, not just to find one single hero architecture.
And so the design variables have changed. Architects are now focusing on things like scaling laws, how predictably a model family's performance improves as you throw more data, more parameters, and more compute at it. And they design these compute-optimal recipes, like the one from the chinchilla paper, which figured out the ideal ratio of model size to training data. It's all about designing a process that scales beautifully.
This is also where ideas like mixture of experts fit in. Now, this might look like we're going back to those old complex designs, but it's not. Mo is a controlled return to specialization. Instead of an architect handcrafting different modules, you have a learned router that directs each piece of data to a specialized expert network. All of this heterogeneity lives inside the stable scaffold we've been talking about, so it adds power without sacrificing that critical stability.
So where has this whole journey taken us? What is the architect's new role in this world?
Well, we've seen the field move from AlexNet's very specific bespoke blueprint to VGG making simple repetition a respectable idea. Then ResNet had its breakthrough with trainable pads, which made truly deep learning possible. The transformer then packaged that lesson into a portable block that scaled across totally different domains. And today, the frontier is designing entire families and recipes that govern how these incredibly powerful models are built, scaled, and trained.
So the architect's job has fundamentally changed. It's no longer about scripting competence layer by layer. It's about defining a scaffold that is sturdy enough for intelligence to actually emerge within it. Which, of course, leaves us with a final, fascinating question. Now that we know how to build the scaffold, what new forms of intelligence is training going to build inside of it?